I'd like to introduce, now here again I completely failed to do the pronunciation beforehand, so I'm going to take a guess at it and you can tell me how correct I was. Liang Zhu from Microsoft is going to present a new method of signing wildcard responses for compact denial of existence by using a fabricated NSEC record, which brings several operational benefits. And we asked beforehand, and this is something different and new.
Hi, I'm Liang. I'm a software engineer at Microsoft. So here today, I'm going to talk about a new way to sign the wildcard response in the context of compact denial of existence. So in general, DNSSEC online signing is very expensive. Because it costs more CPU for each query, and also it can make server throughput worse and also add more query latency. And there are some studies showing that, so basically in some cases, so DNSSEC online signing can only achieve about, so it's about 50% of less of the throughput compared to the response that are actually signed offline. So basically, one optimization is to have a kind of signature cache. So basically, when the server sees the query for the first time, so it can just do the actual signing on the fly, and it can store the signature in the actual memory. So now, if the server sees if the server sees the query for the second time, it can just read the signature from memory, right? Now, if the actual signature cache ratio is very high, so basically everything just stored in memory, so the performance could be very good. Just very briefly about compact denial of existence. So for the actual wildcard match, so the server will actually claim the query name exists in the zone. And it will not indicate it, so it is from wildcard expansion, like the response signed offline. And also for other non-existent names, so the server will use the immediate successor of the queue name as the NSEC next name, and basically just add a 0 before the queue name. But this approach is good. So we can make the actual the actual response could be very small with the algorithm 13 ECDSA, so it's all good. However, so the wildcard response can make the actual signature caching basically a little bit challenging. So the reason is, so it's very easy for one person just to actually easily generate a lot of random query names that can match with a kind of wildcard record. And for the server, it's very hard to actually identify those attack traffic. And so the server has to do the actual signing on the fly for every single query, right? Now, since the query name is kind of unique, so the actual signature caching will not work at all. So how do we solve this? Problem? So can we actually use wildcard signature in basically in online signing? So the answer is yes. So actually, DNS protocol supports that. So for the offline signing response, we can use wildcard signature, and we can use the label count in the NSEC record to actually indicate the signature is from wildcard record. So for online signing, so we can do this as well. So there's no problem. So basically here we just solve one problem. So we can use a wildcard signature to actually prove that response. However, we have another problem now. So here now server says I don't have the record. So actual answer is from wildcard is actually from the actual wildcard expansion. So the server has to provide a kind of NSEC record now to actually prove that answer. So here we need an NSEC record in the wildcard response. However, we cannot use real NSEC record because of the actual zone working. So we don't want to expose all the records. And also, we cannot use compact denial of existence here because the query name can be a kind of unique, right? So if the query name is kind of unique, the NSEC will be a kind of unique. So the actual signature caching will not work. So here really we need a kind of NSEC record. Basically that is actually DNS protocol compatible, and it's also can prevent its own working, and it should be also can be used for basically for a lot of responses. So basically, so it's not one response. So the whole idea is, can we actually fake some kind of NSEC range? So like, for example, can we actually fake a range that is actually smaller than the real range? Say, so if the real range is 1 to 9, and the server says, I don't have record between 1 to 9. So here, so can say that we don't have record from 4 to 6. So the smaller range is still a valid range. And also this range should be large enough to cover many non-existing names, so that this kind of NSEC can be used in actually many responses. And the RSEC for the NSEC can also be cached in memory. So let's take a look at the actual algorithm. So to find to find a new NSEC owner name, we first need to find the actual real previous name. So here in this example, so the ABC is the real previous name, and here the query name is just host. And we try to scan the right. So we try to scan the rightmost label, excluding the actual zone name. And we try to find the actual first different letter. So here in this example, so here A and H are different, then we stop. So we can just simply truncate the string, and we can just append 255. So here now we found a kind of new NSEC name that is actually between the real previous name and the actual query name. And here's another example. So if the actual first letter is the same, so like here, so they're H, so they're same, we can jump to the second letter, and they're different. We just truncate and we just append 255. To find the actual next, the actual next name for the NSEC record. So the overall algorithm is very similar. First, we need to find the actual real next name, and we still need to try to find the actual first different letters in the actual rightmost label. Then we just do a kind of simple string truncation, and we don't do anything else. And here's another example. So basically, if the first letter is different, so if the first letter is the same, we jump to the second letter. We just do a kind of simple string truncation. So here in the example above, we do find a kind of smaller range for the NSEC. However, this range is still kind of large enough to cover many, to actually cover many random names. So this NSEC range can be used for basically a lot of DNS responses, and the actual signature caching can work. So in the method above, so we do use some information from the actual real NSEC. However, we don't want to expose too much information, right? So it can actually enable the actual zone working. So we have a set of rules to actually eliminate the actual information exposed. So like we only search a single label and the actual first two letters, And if the actual label length is too short, and we don't do any kind of so the NSEC fabrication. And here are some examples that we cannot do the NSEC fabrication. So like the actual common prefix is too long, and all the actual that label length is too short. So what happens if we cannot do the NSEC fabrication? So we can just fall back to the original. Fall back to the original compact denial of existence. We can just let server do the actual signing on the fly, and the server will just claim I have the record. And here is a kind of example zone. And if the query name is host, the actual NSEC next name is the actual host 1. So here the common prefix is too long, so we cannot do the NSEC fabrication. So we'll just send a response say basically it says I have the record, I will do the signing on the fly. So there are some exceptions so that we don't need to do the NSEC fabrication. So like for this example zone file, so if the query name is 123, the actual real NSEC the NSEC previous name will be the actual wildcard record. Now so in the response, so we'll use the wildcard signature. So basically the server already tells the client, I have this kind of wildcard record. So we don't need to do fabrication for the wildcard record. And also, for example, so if the query name is XYZ, so the actual NSEC next name will be the actual zone name. So the DNS zone name is not a kind of secret typically. So we don't need to do any kind of thing for the NSEC fabrication. So we just use that. So how does this method work with the actual real world data, right? So we did some simulation with a very large sample of zones host. So they host the Azure DNS, and for each wildcard record, we just simulate 1,000 random names. So basically, so we simulate 1,000 random names with the actual wildcard expansion, and we test to say so if we can do the NSEC fabrication or not. So for zones with a single wildcard label, so the actual result is good. We can say about so it's about 94% of them have more than 90% success rate. So basically our method works with this scenario very well. However, so for zones with the actual multi-label wildcard, so like star.abc.zone name, we only see about so it's about 13% of them have more than 90% success rate. So the result is it's not ideal. So the actual reason is that for those zones, there are a lot of records have the exact same common prefix. So we cannot do the NSEC fabrication. So we also validate our approach with the actual recursive resolvers. We have a simple prototype, and we run that as the actual authoritative server, and we set up an end-to-end delegation for a DNSSEC enabled zone, and we just send a bunch of queries to bind and also unbound. And from the response, so we can see the AD bit set. So basically, the response is authenticated. So our approach is so it's actually DNS product compatible. So there are some open questions. So what would the actual recursive result behave if there are a few different signing approaches? Say if one authority is using this new approach, but the other one is using the original compact denial of existence, how would the recursive resolver will send the actual response? And we need some experiment to actually understand that. And another open question is, can we actually explore the similar idea with NSEC wirelines? Like we can just shrink the actual range for NSEC 3, and also with some kind of random numbers, so that this NSEC 3 can also be used for basically many responses, and the actual secondary caching can work. Here in summary, so here we propose a method of doing wildcard signing on the fly. Because that method is actually DNS protocol compatible, and we can reuse the cache, and we can reuse the actual cache signage in some cases, and potentially so it can improve server performance. And we would like to hear feedback from you.
Any questions?
I have.
Hi.
My name is Roy Adams. I still work for ICANN. I like the idea. I like the fact that you only have to do it in the authoritative server. Mm-hmm. Caches will work, validators will work. No optimization needed on that side. So you can do this on the right-hand side, on the authoritative side. So that's really, really good. It's cryptographically safe. That's good. You can truncate the owner name of the NSEC records. Absolutely. If you want to have and I stood up before I saw the future work on NSEC 3. So my tip was, if you look at NSEC 3,
yeah,
the set of, the frequency of common prefixes, mm-hmm, right, will be more evenly distributed because you're using a hash function.
Yes. And
therefore, yeah, everything is more evenly distributed. You don't have, for instance, like 5 common characters in the prefix if your zone is short. Mm-hmm. So it's a more efficient way of doing things. I'm not recommending to use NSEC 3. It's just it looks to me that it's even better than you're proposing with NSEC. So I like the idea. Well done, and love your presentation. Thank you.
That's all right. Thank you.
Hi, Ben Schwartz.
Yeah.
So, if I understand correctly, this is equivalent to essentially inserting a large number of intermediate names between each pair of adjacent names in the zone.
Yeah, you can think of that way, but the actual name does not exist.
Right. So it's equivalent to essentially, instead of using a single NSEC record to cover the span, we're using a larger number of NSEC records, each covering a small segment of the span between each pair of names.
Right.
And I think that view makes it clear that there's a tunable constant here for the number of intermediate nodes of that kind that you create, which could be large or small. We could add just one node in each span, or we could add millions.
So yes, but so the actual fabrication we did is actually also depends on the query name.
Like, yes, I understand, because we're talking about carving up the query space, and so you have a particular heuristic that generates some number of intermediate points between each pair of names.
Yeah.
In my view, this does not result in any defense against zone walking. So I don't know why it doesn't create an effective defense against zone walking. That is, it only gives you if you have k intermediate points, it gives you a factor k defense against zone walking. And for comparison, NSEC 3 gives you essentially an order 2 to the 128th defense against zone walking. The k value here, instead of being cryptographically strong, is in the hundreds or maybe lower.
So we don't expose the actual NSEC record here, right? So we just do some string truncation. It's not the actual the NSEC record. So the actual name does not exist.
Right, but you ultimately have to return an NSEC record. Basically, what I'm saying is that I think that zone walking attacks still work well against this. They're slightly less efficient than classic NSEC, but I think that I could actually enumerate the zone.
So how you can enumerate the zone? How?
By getting an NSEC record back with 2 falsified names, and then incrementing my queue name to be slightly past the end of the span, and walking hop by hop until I get to a real name. Yeah, we have some limitations there. So we only fabricate. So we only search the actual first two letters.
So we only expose the actual first 2 letters of the real NSEC record here. So if that makes sense.
Okay, but you can't serve an NSEC record that actually spans the real name. So I can continue to walk, it's Zeno's paradox. I can continue to walk closer and closer to the real name. Eventually you will have to reveal the real name,
No.
since there are only 256.
No, so basically in that case, we will not do the NSEC fabrication. We'll just use the original compact denial of existence. And we'll just sign that on the fly. So basically we don't expose the actual NSEC record at all.
Okay, so you're saying once I get close enough to the real name,
Yes.
then you'll
So we just
switch
stop.
to compact denial
Yes,
of
yes,
existence. Okay, thank you.
Shuman?
Shuman Huck, Salesforce. Thanks for doing this work. I think this is an interesting idea. My question is, so Azure, my understanding from talking to your colleague, just very recently implemented DNSSEC,
Yes.
compact denial of existence.
Yes.
This is something you're exploring, right? You have not implemented this.
Yeah, so this thing is totally experimental right now.
Yeah. Okay, got it. And my other question was, what was my other question? Okay, yeah. So your question about testing to make sure validators are okay with this.
Yes.
Kind of the DNSSEC protocol community already knew that it was, because we've discussed whether when we developed the multi-signer DNSSEC specification, we already knew this would be the case. There would be mixed modes of NSEC out there in the field. It's already been field tested and it works. So the new thing you're proposing here is mixed modes of NSEC within the same implementation. So that, in theory, should also work fine. It hasn't been field tested as well, right? But maybe you're going to do it for us.
Yeah. So I think your next theory should work, but we need some experiment to understand that to actually prove that. Right?
Yeah. Okay. And then as far as quantifying the effect, you said you did some simulations with some Azure zones.
Yes.
I would encourage you to better quantify the effect in the real world. Look at resolver traces, right? What they actually queried, and see whether if you had this technique deployed at the zones, how much effect you would get.
Yeah, I think it all depends on the actual traffic pattern, right? So if we happen to have some name, so there's sort of so they have the common prefixes.
Yep.
So then we cannot do the NSEC fabrication. So basically our method will not work.
Okay, great. And if I can slip in one tiny thing, the original reason that compact denial of existence was defined in this way was they wanted to shrink online signing and minimize the packet as much as possible, right? That's why if you answer, if you pretend that the name explicitly existed, you don't need the additional NSEC record that does the wildcard cover, right? So that was the original argument.
Yeah.
I don't know if that's a compelling argument, but I'm explaining that's why the protocol is stated in this way. Right?
Yeah. So here the reason we do this, we want to actually to actually explore this approach is because we want to have the actual signature caching work, so we can cache the actual signature.
Yep. Understood.
Yep.
Thanks.
So I'm going to have to draw this to a close because we have reached the end of this session. I'm going to suggest that the guys that want to carry on talking about this gather themselves together over coffee, because we do now have a coffee break. So please would you extend your thanks to our speaker.